which is just an intro to probability. So there's just a handful of terms we want to get through, and then we'll start doing some basic probability problems. And then after that, we're going to make it a little bit more advanced. Okay, so to begin, we have a bunch of terms. So the first term is experiment. An experiment is just essentially a trial where we observe outcomes. So a trial could be tossing a coin and seeing if it lands heads or tails. But a trial could also be measuring someone's height. A trial could be just anything where you're making an observation. It could be quantitative, like a height, or tossing a coin where the outcome is categorical. There's two types of data, remember, categorical and quantitative. It's some observation you're making. An event is a possible outcome of an experiment. Okay. A simple event is an event that can happen in only one way. I'm going to check something down here. Okay, so I think I have an example coming up. Yeah. All right, so let's say the experiment is picking a card from a deck of cards. Pick a card at random. Okay, that's an experiment. And by cards, I mean on the next page, this is a deck of cards. There are 52 cards. If you pick one randomly, any one of those 52 outcomes is possible. So that's an experiment. Okay. Now, an event is a possible outcome, as I said. So you could pick a heart. Okay. On a deck of cards, these are the hearts I've just circled here. Okay, all of them with little pictures of hearts on them. Okay, or you could pick a queen. That's another event. Okay. As I say, a simple event can happen only in one way. So if I say you've picked a queen, that actually can happen in 4 ways. And so that's not a simple event. Okay? Or picking a heart, that can happen in 13 ways. So that's not a simple event. Those are called compound events. If I say the queen of hearts, that's just this card here. That can only happen in one way. So that's a simple event. All right, so going back, a compound event can happen in only one way. Sorry, can happen, I'm getting confused, in more than one way. Okay, for like a simple event, as I said, you could pick the Queen of Hearts. Okay, but picking just King is a compound event because there are 4 of these. Okay. Sample space is just a list of it's just a collection of all simple events in an experiment. So this would be like all 52 cards in the deck. That's the sample space. Okay. Any questions about that? So I'm looking to see if any of you have raised your hand or typed anything in the chat box. I've got nothing, so I'm just counting on you guys to weigh in if you have questions. As you can see here, that events are denoted with capital letters, A, B, C, or whatever. The probabilities of the events, we put a P around the event. So P of A means the probability of A, this first one. P of B, the probability of B, etc. Okay. For any event S, the probability must be between 0 and 1. Any questions about that? Ooh. When you say something can happen in only one way, is that the same as resulting in one data point? Now, so a data point is sort of a variable. This is for Jonathan. A data point is a variable, and it's actually the observation, because, sorry, the data point is actually the experiment, where there's some observation you're making, which you could call a data point, but there are many outcomes for the data point, the experiment. So when I say an event, that's the outcome of the data point, whatever the actual observation is. Now, if you think of the data point as being someone's height, an event would be that the first person is 6 feet tall, exactly. That's a simple event because a person can only be 6 feet tall one way. But if I say the event is you're between 5 and 6 feet tall, that's something that could happen. It's an event if it happens. But being between 5 and 6 feet tall can happen lots of different ways. There are many ways to satisfy that. So that's a compound event. Jonathan, you okay with that? You could give me a thumbs up. Where'd you go? Yeah, that makes sense. Cool. Okay. So then going back down, we say any event, the probability has to be between 0 and 1. And we'd say, if you use percentages, 1 is 100%, and 0 is, of course, 0%. Okay. Just a couple comments down below here. Probabilities near 0 are nearly impossible, but not impossible. Okay. Probabilities equal to 0, that's impossible. Okay. Probabilities near 1 are nearly certain. And probabilities equal to 1 are certain. Okay. Then, so that's just a quick intro to the ideas. And if we go on to the next page, we're talking about the probability of an event. Okay, so this is called the classical approach. It's the most simple of the approaches for computing probability. It says if an event can occur in capital X simple ways, and again, you're counting simple outcomes, in an experiment with a total of n outcomes, the probability is X over n. And I'm using a capital X and a capital N. Later on, I'll change the notation for that. Okay, so we'll do examples down below here, but the idea is, like, if the probability of getting a king is 4 out of 52, the event is king, but that's a compound event. Getting a king can happen in 4 simple ways. I'll circle those here. Oops, I'm getting confused. Okay, so you can get a king in 4 simple ways. So that's the numerator of the probability, 4 ways. In an experiment with 52 outcomes, so you would just say 4 divided by 52. Okay, I'm looking for questions about this. It's easiest if we just do some examples. I don't see any hands up, so we're going to keep going. There's a rounding rule here, and this is something you just have to kind of get accustomed to. This basically, you have to keep what we call 3 significant figures on probabilities. This is for probabilities or percents or proportions, which are all really the same for us in this class. Okay, that is, I want you to keep 3 significant figures. When you round. And then I might just say the figures are significant when you don't count leading zeros. So that just means don't count leading zeros. Okay, those aren't part of the measurement. Those are mostly placeholders. Okay, and so, you know, I'm just going to do some numbers above this. If you do like 0.123, that has 3 sig figs, we say. 3 sig figs, which is easy. But 0.000123 also has 3 significant figures. Okay, so I want to make sure you guys understand that. So I'm going to pause for a second and see if there are questions.
Professor?
Again, you just don't count the leading zeros.
Professor?
Right. Yeah.
In my chemistry class, we're learning about sig figs also. Hey, buddy. So after, if there's not a decimal in a number, so like the number 100, no decimal at the end, that would have 1 sig fig because the trailing zeros don't have a decimal at the end. Does that apply here as well?
Trailing zeros, okay, now the 100 has 1 significant figure if the 100 is rounded. I think I can, hey, who is that talking?
That was me, Jason.
Hey, Jason. I think what I'll do is say this. In statistics, it's easier than in chemistry because mostly we're worried about numbers after the decimal, because I'm only giving this rule for percentages, sorry, for proportions and probabilities, which are always between 0 and 1. So I don't actually have to worry about numbers in front of the decimal in my rule. Do you follow me? So I get to have a rule for significant figures that's consistent with your chemistry teacher, but I don't have to. It's really hard to understand. And this whole, your example is how many significant figures does 100 have? And I would say it depends. It could be a 1 figure, just the 1 counts, and you don't count the trailing zeros, unless you know that the trailing zeros are not there by rounding. If you know that those 2 zeros are there because they're precisely measured as part of the number and not because of rounding, then they're all significant figures. So
Okay, that makes a lot of sense.
Yeah, so it's just way more complicated in chemistry. Here I just say, just don't count leading zeros. And that's that. Okay, does anybody else want to ask about that? Okay, you guys, I'm not going to be really strict on this, but it's better to be careful about rounding, and don't round too much. I mean, a simpler version of this is just don't round too much. The rule is 3 significant figures. I will do point deductions if you break the rule a lot, but just basically the way I'll do it is if I see you rounding too much, I'll ding you once on an exam, but I won't keep dinging you over and over and over. So you may lose a point for it, but I'm not going to make you lose 5 points if you've done it 5 times. Okay, but it's sort of, it is important. So I want to make sure we're all kind of aware of this. This is because the idea is this one that I just wrote up here, if you round this to 3 places after the decimal, and I hope this makes sense. If you round up to 3 places after the decimal, it rounds to 0. And now you're telling me that this event, if it's a probability, you're telling me the event is impossible, my bad. If you round it to 0, you're saying it's impossible, but it's not. And there's a big difference between unlikely and impossible. And if you think about it in terms of populations, you know, if something has a 1/100th of 1% chance of happening, then that thing will happen to 1/100th of 1% of all people, which will be millions of people. So small percentages are rare, but they're super important in statistics because we always focus on those really exceptional cases in statistics. So we are really interested in these low probabilities, as you'll see. In hypothesis testing, it's always about looking for the low probability events. And those are the ones we call statistically significant. So we're super, super duper careful. Okay, so as far as Jonathan, so for something like a percentage, yeah, so well, I'd rather change your example, Jonathan, and say, look at this one. Okay, I'm gonna write on the whiteboard, or the whiteboard again. So if you have 0.0123, so that has 3 significant figures. This would be written as a percentage as 1.23%, and both of those have 3 significant figures. So, and the rule applies. You count figures starting at the first non-zero figure. So for the 1.23, you start counting at the 1. So you don't actually look where the decimal place is with significant figures. You, in both cases, you would count those as 3 sig figs. Okay, and I'm zooming in on this thing here on the right. It's a little bit too far to the right. Okay, so you'll count 3 figures, whether it's in percentage or proportions, but I don't want to go any deeper into this. I feel like we're destroying it. We're beating it to death. Okay. So let's go ahead and do some probabilities. And just so that you guys know, some of you guys are thinking, well, can I just write maybe you're thinking, can I write my answers as fractions? Yes. Can I write my answers as a number between 0 and 1? Yes. Can I write it as a percent? Yes. I'm not really asking you to write these in decimal form, and I think it's almost better if you don't sometimes, because it just drags it out. These problems aren't that important computationally. They're important theoretically. It's really about the ideas right now. We're not going to use many of the rules as we go forward, but I need you to understand the basic ideas. Okay, so let's not beat this to death. As you can see, we've got the deck of cards up here. The experiment is to pick one of those 52 cards at random. First example says, let A be card is a heart. Is it simple or compound? Anybody want to pipe in and say, or type it in? Getting a heart, is it simple or compound? Good, it's compound because there's 4 ways. Remember, compound means it can happen in more than one way. So because it can happen in more than one way, it is simple. Did I say simple? Oh my God. I'm not trying to confuse you. It's compound. So it can happen in 4 ways. Okay, then B, card is a queen, simpler compound. Again, this is compound. And you guys want to correct me on the mistake I made above? How many ways can you get a heart? 13. So, oh God, I'm going to try not to do this. I'm sorry, you guys. 13 ways to get a heart. Yes, that's these guys up there. 13 of them. But to get a queen, also compound, there's 4 ways to do that. Okay. But then it says A and B. A and B. That's the Queen of Hearts. How many ways can you do that? Just one way, right? So simple. Right. Any questions? Okay, so now we do these probabilities. So when you look at A, it says the card is a heart. We already said that can happen in 13 ways, so it's 13 out of 52. Somebody type in probability of B. This is the probability of getting a queen. And write it as a fraction, something divided by something else for probability of B. Yep, 4 divided by 52. Now, A and B, if you look up above, we already defined what A and B is. That's the Queen of Hearts. And by the way, you notice I'm not reducing my fractions, you guys. In this class, I almost like it if you don't reduce. I'm not telling you not to reduce your fractions. I am saying I don't care if you don't reduce your fractions because you almost lose information when you reduce your fractions. When I see 4 out of 52, it's like, okay, it happens 4 different ways out of 52. If you reduce it, then that information is obscured. So I'd almost rather you didn't, but I don't care. Okay, so for A and B, people are saying there's only one way out of 52 to get a Queen of Hearts, as we said. Now, A or B, I want to see if somebody feels like explaining why it's not, this is wrong. Why is it not 17 out of 52? Okay, there are 13 ways for A to happen. There are 4 ways for B to happen. Why aren't there 17 ways for A or B to happen? You can unmute yourself or type it in. Well, keep trying. Okay, I'm gonna just sort of circle this. A was heart, wasn't it? Or was it queen? A is heart, and there are 13 of them. So I would count all those. I think Nicholas is yeah. Susan, you've got it. The queen, there are 4 of those, and Susan's saying some ways are duplicated. In fact, the Queen of Hearts was counted twice if I do 13 plus 4. You guys follow on that? Yeah, there's an overlap. Exactly, Jonathan. Way to go. Okay, so the 17 out of 52 is wrong. It's 16 out of 52. Okay, now there's just a couple of things. So, basically the note I would add on probability of A or B is don't double count anything. Then the thing to notice about the probability of A and B is these are going to turn into rules. or formulas. And I would just say the formulas are important theoretically, but people tend to get themselves in trouble with these formulas. I just want you to notice you've computed probability of A and B using the simplest formula of all, just the ways it can happen, divide by the total number of outcomes. I'm going to show you another way to compute it, but you don't need to do this. And it's almost ridiculous when you do. But probability of A and B, we said, is 1 out of 52, which is, if you remember, 52 is 13. It's 4 times 13. Okay, and the reason why I'm doing that is to remember the probability A is a fourth. 13 out of 52 is a fourth. And the probability of B is 1/13. You're kind of seeing that come up in the probability of A and B. It's a fourth times a 13th, which is the probability of A times the probability of B. Oops. So probabilities just do that. It's a strange, interesting thing, and it's not hard to explain why it happens. Okay, now Yamaleth is saying, where does the 52 come from? Yeah, again, there's 52 cards in the deck altogether. So when we do the most basic probability computations, you're taking the number of ways I think up here it says S. So I won't say A, I'll say S. The ways S can happen. And you're dividing by the total number of outcomes. Okay, so for the deck of cards, there's 52 outcomes. Is that okay, Yamaleth? She says yes, okay. All right, so anyway, the real critical idea is the probability of A and B is equal to the probability of A times the probability of B, and that'll play out in some theoretical discussions. The probability of A or B is the 16 out of 52. And if you think about it, I originally said, well, that's really the 13 out of 52, which are the hearts plus the 4 out of 52, which were the queens. Now that's an overcount, but it's because I've counted the Queen of Hearts twice, that's 17 out of 52. But then if you subtract out the overlap, which is the 1 card out of 52, that was counted twice, that's the probability of A and B. You can see that the probability of A or B is just the probability of A, that's the first one, plus the probability of B, that's the second one. But then if there's an overlap, you have to subtract out the probability of A and B, like that. So that's going to be called the addition rule. Any questions about any of that? So these are going to become rules, and we're not going to really use them. Okay, so they come up once or twice, but they're not very important, and it's better if you sort of avoid it when you can. I see somebody's highlighting. Does that mean there's a question? Okay, I'll take that as a no. Yeah, definitely, and I should say, you've got, there's a whiteboard, right? So if you go in to annotate on this, you can, especially if you're asking me a question, you can highlight things or draw on this as long as you remember to erase it when you're done. Okay. Going on, we're going to do, and by the way, these are theoretical probabilities. If you think about it, there was no real deck of cards here, and nobody picked a card. And I should say, this, if you could go back to the top of this page, where it says X can occur in, sorry, S can occur in X simple ways. Could we make a comment here that this requires that all, so let's say this, assumes all simple outcomes are equally likely. That's really important, and I forgot to put it in here. But if you think about the example down here, it says pick a card at random. At random, we've defined that. Random selection means that all outcomes are equally likely. So when I say you're doing this at random, I'm saying you are following the rule that's required so that we can do our computations here. If all outcomes are not equally likely, then that's the definition of a biased selection, and the bias is selection bias. But all of statistics assumes that selection is random. And if selection is random, then we can compute probabilities based on this discussion that we're having right now. If things aren't random, then you can't do anything with probability. So pick a card at random. So this, again, is assuming all outcomes are equally likely. Okay. I'm going to just pause and see if there's any questions. Okay, so again, that whole approach was called the classic approach. And it's not an approximation for probability. Those are exact probabilities as long as when you're doing your selections that they're random. If you have true randomness, then this method works. The problem is that lots of times things aren't truly random. You know, if I say pick a person at random, what's the probability that the person is a female? And that's complicated because there's actually more females on the planet than there are males or other gendered people as well. Female people live longer, and so they're slightly more probable if you pick one at random. So you can't just assume it's a 50-50 outcome. So this thing of all simple outcomes are equally likely. It's a pretty complicated statement, and lots of times it just doesn't work. A simpler example is I say flip a coin. You know, what's the probability that it lands heads? Well, I would like to say there's one way to get heads out of two outcomes, but I don't know that heads and tails are equally likely. So I can't say the probability is 50% exactly unless I'm certain the outcomes are equally likely. And I see a comment down here. It says from Susan, in this example, would a biased selection be a deck of cards with all the spades removed? No, I think on that one, a biased selection, see, if you remove the spades, all you're doing is you're limiting the sample space. So the outcomes, I mean, you could say, if you tell somebody, no, I'm gonna actually change my answer. If you tell somebody that all 52 cards are there, but the spades are removed, then the probability of spades is going to be reduced to 0. And if they think the spades are there, then the probability of a spade is now lower than the probability of the other outcomes. So you don't have a random selection if you're talking about the entire deck. So I think that's pretty good, Susan. I'm going to agree with you. And then the other thing I think I'd say is another way to do a biased selection from a deck of cards is to not shuffle the cards. So you could put anything you want on the top of the deck. And then if you just ask someone to pick a card from the top of the deck, then obviously that's not a random selection if it's not shuffled and you don't let them pick anything they want. So then the probability, you know, let's say the card on top is a Queen of Hearts, then the probability of a Queen of Hearts is 100%. And that's introducing bias. So that's not random. You kind of need to shuffle the deck, and you kind of need to allow people to pick any card they want, and then that's a random selection. Any questions, anybody? Is Susan, you okay with all that? Awesome. Okay, we're gonna go ahead and do our probability experiment now. So, and this is gonna be for all of us. So I'm gonna go back to Canvas real quick and point to this page. Actually, I can do it this way. So the web page is, it's got, with one T, and it's not me, it's my office partner who did this for me. It's got childress.com/games/ and the game is called Porkability, which is just hilarious. So he called it Porkability. Like that. And obviously that's how you spell porkability. Even though it's not a word, it has the correct spelling. Okay, so if you can get to that, I'm going to give you a second. And if you're not able to do this, I understand. Susan Faith, you have your hand up. I'm guessing that's from before. But if you have a, she'll fix it. Okay, no worries. Okay, so the Porkability app, I'm gonna stop the share here real quick. And as again, see what I was supposed to do is bring these little pigs to class, but the pigs are carriers of the coronavirus, as you know. So the pigs are in quarantine. They're being. It's not self-quarantine. I'm forcibly quarantining the pigs. They're filthy. They're absolutely filthy. So we have to use virtual pigs. So I'm going to go to my. I'm going to share my screen for Porkability real quick here. Okay, so I hope you guys can see that. And I'm also, once again, trying to find my chat. This keeps happening to me. There it is. Okay. All right, so basically the pig dice, actually, the pigs are dice, and when you roll them, they land in 6 positions. And the positions are here on the screen: side, left side, right side, on their back. That's what we're going to be counting here. When the pig lands on its back, that's going to be considered a success. The trotter is just when he lands on his feet, and that does happen. I think it's a she, though. If you look very closely, I apologize. Snouter, they can actually do sort of a headstand for the snouter, and the leading jowler is a miracle when it happens. The pig is on 1 foot a nose and an ear. It's a joy when it happens. Okay, now if you scroll down here, I want you to toss your pig 25 times. So you just tap and it records the outcomes. This one landed on, my first one landed on its back. Next one, again on the back. This one's a trotter, it's on its feet. You just keep tossing. So fill that up for 25 outcomes. These are random. And the applet is respecting the true probabilities. And when I say true probabilities, I think the probabilities depend on the individual pig. And every pig is different, as you know. And so the probability the pig lands on its back sort of depends on the pig. And sometimes you're going to get loads and loads. I mean, see, if you look, I got 1, 2, 3, 4 where it landed on its back. If I do it again, 1, 2, 3, oh my Lord, 1, 2, 3, 4, 5. I got 5 that time. So last time I did it, I got 8. I actually did it 2 times in a row and I got 8. So it's sort of, you know, it's random. But in the long run, yeah, you got to lean. Congratulations, Jason. Wow, that's terrific. If I had money, I would give it to you. I actually do have money, but I can't personally give it to you right now. So anyway, so you get these outcomes. I'm sorry. So anyway, we've got these outcomes. And what I want you to do real quick is to go back to the handout. So now I'm going to do a new share. Of my iPad. Okay, and then what you're going to do is just write yes or no for the 25 trials. Yes means the pig landed on its back. A success is the pig landed on its back here. So I want you to go back, look at your trials, write yes if the pig landed on its back, write no if it didn't. You can just fill up the table for your little piggy, and every pig's different, as you know, as I've said. So I'm going to go ahead and put in my results, just sort of quietly here. Okay, so I've got mine in. Trying to find my screen. Okay, so I've got mine in. And what you want to do is count up how many successes you had at a given trial. So, and these should accumulate. So on trial 1, I had a 0 because I didn't get anything. On trial 2, I still have a 0 because I still haven't gotten it to land on its back. And you would only increment this when you get a yes. So in trial 7, I had a yes. So now I've had 1 success. I got another yes, so I increment. Now I have 2 successes. I get another yes, now I have 3 successes. And then the no's start coming again. So I'm still stuck at 3 successes for some time. There's a yes on trial 18, so I'm up at 4. And no successes, so I'm stuck at 4. To trial 24, where I'm at my 5th success, and that's all I got. So do yours something like that. Just increment when you see a yes. Now, the relative frequencies are the successes divided by the number of trials. So let's go ahead for relative frequency. I'll define that here. It's the number of successes divided by the number of trials. I'm wondering, do I need to, hey, do you guys want more time? Would you chat a yes if you need more time? So I'm gonna say that nobody needs more time. Okay, so with relative frequencies, you're taking number of successes divided by number of trials. The number of successes is in the third column of the table. I've highlighted that with the green highlight. And the number of trials I'll highlight with blue maybe. So there was 0 out of 1 on the first roll. So the first proportion is 0 out of 1. That's a relative frequency. And then 0 out of 2. And this just goes on. 0 out of 3, and so on. Finally, on the 7th trial, I get to say there was 1 success out of 7. Then 2 out of 8 on the 8th trial. 3 out of 9 on the 3rd. So you're dividing in every case, the number in the 3rd column by the number in the 1st column. Okay, I'm looking to see if anybody has questions. Okay, so just go ahead and finish this. Yeah, no, we're going to divide these. So you want to get your calculator out. Normally, I would say 3 significant figures, but right now, just do 2 places after the decimal because we have to graph these in a sec. So, you know, the beginning is really easy. On the first one, you're either going to have a 0 or a 1. So some of you guys are going to have a 1. So for 0 divided by 1, that's just 0, and so on. So then we're going to do a graph after this. And I'm just copying my numbers over because I can't see them on my iPad. So I'm just going to graph these and cross them off as I get to them. Just a couple of points here. Start at 1, not 0 on the horizontal axis. So the 1 here, don't graph anything for the 0. 1, 2, I'll just put the odds in to make it easier to see. Okay, so got all my trials in. Again, don't start at 0. Does anybody have any questions? I don't see any questions. Perfect. Okay, so I get a bunch of zeros till, I don't know, 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6. Seventh trial, I got 14%. Then eighth, 25%. Ninth, 33%. It's not really necessary to make this into sort of like one of these stock market graphs, sort of a time series. I'm going to do this just to kill time so that people can catch up. But the dots are sufficient. Okay. I'm looking to see if anybody has questions. I think I can get rid of all that. I don't know the probability that the pig lands on its back, but I've got a sense of it right now. You guys all good? Maybe give me a thumbs up if you're ready to go, or a green check mark if you're ready to go. Thumbs down. I'm gonna give Andrea a second. Wait, now your thumbs down is gone. I'm just gonna wait another second, you guys. Susan's good. And again, all you guys, I'm just waiting for either a thumbs up or a check mark. When you're ready, you can finish and then post one of those when you're ready. It's almost break time, so we'll be doing a normal break in a little bit. All right. If you need more time, will you type that as a message? I'm happy to give you more time. Okay. I'm going to go ahead and jump ahead then. Now, when it says here, what's the probability that the pig lands on its back? What do you think? Are we going to be estimating this, or do we know the probability? Go ahead and answer what you think the probability is right here for the pig landing on its back. Now, to me, if somebody asked me, now some of you guys probably got in the 30% range. I got close to 20%. Last time I did this, I got 32%. Okay. But today, I'm closer to 20%. I actually feel better about the 20%. So I'm just going to guess and say around 0.20, because that's the last relative frequency I got way up here in the table. I got 20% toward the end, and that seemed to be sort of stabilizing. And the real thing that you want to notice here is just the way the probabilities sort of are, they vary a lot in the beginning, but they stabilize over time. And that's what you're looking at when you look at these graphs, is the law of large numbers, which just says these will stabilize if you can get more trials in. So I'm guessing around 20% because that's what my last figure, but you guys might have different ideas about this. So put down whatever you like, but I'm gonna say 20%. Now, anybody wanna type? Oh, Susan got 16. Anybody wanna type in whether you think this is exact or an estimate? Yeah, everybody's right. This is an estimate. Oops. Then tell me how you would be more precise in this. If it's just an estimate, how would you make it better? More trials, correct. So that's sort of intuitive, and people kind of get that usually. That's the law of large numbers. So as the number of trials increases, the relative frequency of an event approaches the true probability. And then I might say that we will never really know exactly the true probability. Actually, I'll leave that out. But generally speaking, whenever you use relative frequencies to estimate a probability, it's always just an estimate. Okay, so going back up, I don't think did I fill everything in here? Yeah, skip something. So go back to the previous page. Okay, so it says estimating probabilities using relative frequencies here. And it says if we conduct an experiment n times and event S occurs x times, then the probability of success is just x over. Okay, and again, that's called a relative frequency. And it's just an approximate probability. And unfortunately, in statistics, we never know true probabilities, so we're always looking for ways to sort of just approximate them. Okay. You're pretty good here? All right.